great pleasure to have here Dr. Kyriakos Vamvoudakis. Kyriakos is with the Department of Aerospace and Ocean Engineering at Virginia Tech, where he serves as an assistant professor, although his publication record rivals that of an associate professor with 2 books and 31 journal papers. Kyriakos' interests are on approximate dynamic programming, game theory, and optimal control, with applications to cyber-physical security, network control, smart grids, and multi-agent optimization. Kyriakos received his diploma from the Department of Electronics and Computer Engineering from Technical University of Crete in 2006, and then he did his master's and PhD degrees in 2008 and 2011 respectively at the University of Texas at Arlington under Frank L. Lewis. From 2012 to 2016, he was the project research scientist at the University of California, Santa Barbara. Kyriakos has obtained several awards, including the 2016 International Neural Network Society Young Investigator Award and the Best Paper Award for Autonomous and Unmanned Vehicles at the 27th Army Science Conference in 2010. Kyriakos is an associate editor of the Journal of Optimization Theory and Applications, and he's a senior editor for the IEEE. Kyriakos.
Thank you very much, Nico. Καλά, είναι ευχαριστησή μου να είμαι εδώ πέρα. Αποφοίτησα, ήμουν εδώ πέρα από το 1 μέχρι το 6 και από τότε δεν έχω ξαναέρθει στα Χανιά. Οπότε ο Νίκος μου έκανε αυτή την πρόσκληση να έρθω και ήταν μεγάλη μου χαρά να δω φίλους, να κάνω νέους φίλους και αυτά. Λοιπόν, Νίκο, είπες πολλά, όχι τόσα πολλά. Λοιπόν, όπως είπε ο Νίκος, είμαι assistant professor στο τμήμα αεροναυπηγών του Virginia Tech. Υπάρχουν μερικές ορολογίες, οπότε θα την κάνω shape towards English την παρουσίαση. Ο τίτλος της παρουσίασης είναι Data-Driven and Resilient Learning Algorithm for Autonomous Cyber-Physical Systems. Φαίνεται ότι έχω βάλει τα buzzwords εκεί, θα δούμε αν τα κάνω handle later. Λοιπόν, Νίκο, αυτό το slide είναι για σένα και για τις ωραίες στιγμές που πέρασες στο Πολυτεχνείο Κρήτης. Λοιπόν, okay, so, what is the motivation now? Why do we want to work in such theory and in such systems? So, cyber-physical systems είναι το interconnection between cyber and physical components και μπορούμε να κάνουμε integrate new technologies, sensory data, control data, complex dependencies, sample communication και διάφορα conflict utilities. Και υπάρχουν πολλά application. Από τα application είναι, ας πούμε, από process control networks, manufacturing, ακόμα και economics, energy efficiency, aerospace, power systems, etc. Και υπάρχουν γενικά πολλά project, υπάρχει μεγάλο interest, ιδίως στην Αμερική για cyber physical systems και η NSF, το National Science Foundation, έχει ένα πρόγραμμα γι' αυτό και they're very interested. Οπότε, εμείς κάνουμε exploit, εκτός από το, εγώ είμαι control person, εκτός από το real-time control, κάνουμε exploit και in other parts από τα cyber-physical systems, specifically cyber-physical security, where we try to see and assess the correctness of measurements and the compatibility of measurement equation. There are techniques out there ranging from classical fault detection and adaptive control, but they consider only generic failures. But cyber-physical attacks are worst-case attacks. Of course, we want to differentiate cyber-physical security from cybersecurity. Cybersecurity is ineffective and does not exploit compatibility of measurement data with physics or dynamics. So it takes only the one part, but doesn't take only the physical part. So this combination actually is called cyber-physical security. Okay, and of course, we want to use combination from different techniques. So in cyber-physical systems, since we have lots of data and lots of utilities and conflicting ones, so we want to combine different techniques from control theory, game theory, and network optimization. And so I found this very interesting. So you see that we're actually running towards the fourth industrial revolution. And so this is through the use of cyber-physical systems. So I'm sure you're familiar with the first, the second, and the third one. And now the fourth one is actually, other terminologies is Internet of Things, let's say. It's another word for cyber-physical systems. So I think there's lots of open areas in this component there. Okay, so what we want to do in security, especially in cyber-physical security, is we want to detect and mitigate attacks on control mechanisms. And so we will consider different kinds of attacks, that they can be from sensor attacks to actuator attacks. And we want to combine the cyber and the physical part of the feedback loop. So, we can assume that the signals, the attack signals, can be additive and possibly unbounded. So we don't know the form of the signals. And we want to design effectively the feedback loop such that we are able to mitigate stealthy attacks. Okay, so what I mean by stealth is that the attacker doesn't want to be detected. So he doesn't want to be detected by intrusive detection systems. So, so he wants to be stealth and silently do the damage in our systems. So how he can do that is he can hide himself in a disturbance or in some packages that you transfer through the cloud or something like that. So you will see some things like that in my formulation. Okay, so in cyber-physical systems, so we have the terminology of intelligent sensors. So intelligent sensors are actually in several applications. And what we want to do is we want to detect events, and also we want to measure different things, okay? And then after that, we want to take the steps to mitigate any attacks that they have happened in these intelligent sensors. Okay, so I'm sure some of you might be familiar with the Byzantine Agreement. So the Byzantine Agreement is, you have, it's actually applied in hardware, specifically in Microsoft. It was invented by a guy in Microsoft. And so what this does is you have the top guy in the army, and then you have some majors, and then they tell you if you want to attack or defeat, okay? But you have some traitors inside these people, okay? And so you don't know if they're telling you the truth or not. So you have to decide, based on this uncertainty, you have to decide if you want to attack or not. And, okay, so here's some actually cyber-physical systems specifically for aerial vehicles. So you see that everything is connected with the Internet of Things, and nowadays the drones are almost everywhere, and they communicate through wireless communication. I think warfare will do lots of damage in these things, and so you can see the attacker can actually compromise any parts of this. So any signal that communicates with the UAV, specifically through the smart devices, if they can be compromised. Okay, so the attacks are all over the news about all these things. So now that I have motivated the problem, so we will first talk about detection, and then we will talk about mitigation, and we will conclude and talk about future work. Okay, so first is the detection in adversarial environments, which is based, as I told you, in the Byzantine general problem. Okay, so this is in collaboration with several people. Okay, so let's say I have a bunch of sensors, okay? So the easy way, let's say that the sensors are deterministic. Oops. Okay, so the sensors are deterministic, okay? So of course, if the sensors are deterministic, then I know when to get the right answer, right? So if less than half of them are manipulated, I can get the right answer, okay? So in the stochastic sensors, which is actually the Byzantine problem, without manipulation, so let's assume we don't have any attacks, okay? So if we don't have any attacks, then we can do just the classical hypothesis testing, okay? So, and you see that if I have one sensor, I have one probability of error, but when I have multiple sensors, this decreases, okay? So this is a classical problem. But what happens when you have stochastic sensors with potential manipulation? Okay, so not only I have stochastic errors, but also I have some adversaries that they change the measurements. And I don't know which sensors are attacked, and I don't know what's happening. Okay, and of course sensors are everywhere, so this is, we call this an interesting problem. Okay, so let's now formulate the problem. So let's say that my sensors are binary. Okay, so let's say you have, you're in a room, and then you have, let's say, 10 sensors, and all the sensors are measuring the same thing. Let's say that either is a fire in the room, okay, or if it's going to rain tomorrow, or something like that. So if, let's say that the events are equal in the probability, so of course you know that it's 0.5. But of course, I don't have my x's because I have another thing which I will call y's, and these are the potentially attacked measurements, okay? So I have n measurements, and then some of them are attacked. And of course, this is the probability that the y, so x is my event, okay, that I want to find, and yi are actually the measurements that they come from potentially attacked sensors. Okay, so now I don't know which sensors are attacked or not. Okay, so that's why I will base my observation based on a signal zi. Okay, so zi. So if the sensor is not attacked, it's yi, and then I don't know if the sensor is attacked. So of course we will assume that the adversarial components, they have a limited bandwidth or a limited, a budget, let's say, so they cannot attack all the sensors, which I think it's a reasonable assumption, because if you can attack everything, then you're actually spending lots of resources. Okay? So we will assume that from the n sensors, the m of them are attacked. Okay. So, sure.
Τα noisy measurements είναι εξαιτίας θορύβου ή εξαιτίας attack?
The noisy measurements are εξαιτίας θορύβου.
Εξαιτίας θορύβου. Τον οποίο θόρυβο δεν θεωρείται χαμηλής πιθανότητας από ό,τι βλέπω.
Ναι.
Okay. Ναι. Άρα έχουμε τα noisy measurements εξαιτίας θορύβου και μετά έχουμε τα τελικά measurements, τα οποία γίνονται reported, που είναι τα Z.
Ναι.
Ευχαριστώ.
Παρακαλώ. Λοιπόν, και of course, we're not getting attacked every day, so we have to associate the probability of attack that we're being under attack. So of course, this is very hard to know, so you will see that our interpretation of sensor data will be mostly dependent of the probability of attack. Okay, so, and, so this probably answers also your question. So here you have the y's, so these are the measurements, the noisy ones, and then they're attacked, and then you have something else which you call Z, which we don't know what's happening there. And then we have to find estimation policies and then estimate the event. Okay, so what we want to do is actually we will formulate this as a zero-sum game. Okay? So what I mean by that is that we want to estimate this x hat, this x based on some x hat given measurement zi's. Okay, so, and as a detector, okay, so we want to minimize that. And the potential adversarial component wants to maximize that. Okay, of course, this is a huge problem, okay, and because there's different combinations that you can attack. Of course, you can consider that as if you consider 0 ones, you know, as you increase the number of sensors, this increases exponentially. The minimizer, which is actually the detector, x hat, actually picks one of the possible estimators of the event x. And then the attacker, which is actually the maximizer, selects an attack policy. Okay, so this attack policy, of course, is where to attack, how to attack, and what measurements to put in these attacks. Okay. So of course, this also is huge, okay? So I mean, there are ways to solve this kind of problem. So if you put all these components in a matrix, and then you solve the game in a matrix form, okay? But this increases exponentially as with the number of sensors and the number of attacks. So it's not that easy. So what we want to do is we want to find effective ways to actually reduce this gain and then have a confidence level that we actually will detect the event. Okay, so let's do some symmetries. You will see that later I will just take over these assumptions. And so let's say that we have some symmetries. So in other words, all sensors are equal in their probability of error and vulnerability to attack. So you will see that this will be deleted pretty soon. We can also reduce the matrix of the gain with policy domination. So we'll check every policy, we check the cost that comes, and then if it gets a lower cost, we just remove the policy, the rows and the columns. Okay. So, and of course we will do the second assumption, which is actually, so the attacker has two possibilities. So which sensors to attack and what values to put. So we will actually do that by saying delta which of x and delta how of x. So of course, the attacker, we will also assume that he knows the event x, okay? And he will try to confuse us. Okay, so by doing that, these symmetries, so we can reduce.
How come he knows the event x? How
Hmm?
come he knows the event, the real event?
Usually when you do cyber physical securities things, so you know actually the attacker has inside information about things. I mean, if he doesn't
He knows
know.
more than you.
Yes, yes.
Or is that just the worst case to fight again? I mean, it's the worst case and the best, the best skilled attacker.
Yeah, of course, we will also assume that the worst case scenarios, that he knows the event. So if he doesn't know, then he has, I mean, we are equal then. But we will also, mostly in cyber physical security, we assume that the attacker knows actually the true event. So he will try to confuse us by putting some other values there.
Yeah, my question is that because we can really assume that he really knows it, or is it just, a worst case to deal with so that less
Oh yeah, of course, this is the worst case.
cases will be automatically.
Yes, the worst case. Of course, I mean, he might not know it, but this is the worst case. We have to always, because this is the worst case attacks, and game theory is always worst case scenario, so we will assume that he has the best knowledge, more knowledge than us. So, of course, by doing that, we can reduce the size of the matrix of the game by significantly to these estimates and these attacks. But we can do even better than that. So this is just by exploiting symmetry. So let's say that I have three sensors. I have 0, 0, 1, of course, okay? So this can be treated dually with 1, 1, 0, okay? So if from 0, 0, 1, I pick, let's say, 0 by majority, in the other case, if I have the dual of it, I will pick 1. Let's say this simple case. This is just a simple symmetry to reduce the components of the matrix. Okay, so of course, still we can do better than that. I mean, yeah, of course, since we can just construct the matrix for that, and we will, of course, we will assume that the policies are mixed. So the mixed policies is that every policy will follow a distribution, okay? Because pure policies, they don't exist in such games. Okay, so, but now we can do even better. So we can actually reduce, for a specific probability of attack, we can actually reduce the game to a 2x2 matrix. So we found this probability of attack, which of course we will actually want to know later. But let's say that for now, we have very small probability of attack. So we know that we can reduce actually the matrix to a 2x2, okay? And you will see what are the policies and scenarios. And so also the other interesting thing is the optimal, you remember this probability, okay? So you remember that if I don't have any attacks, then it comes to the hypothesis testing, the classical hypothesis testing. If I have probability of attack, then you see that this actually increases linearly, of course, as you expect the probability of attack, and exponentially with the number of attack sensors, which is actually something that intuitively seems that it's logical. So, so now let's see what are actually the policies, the two policies, because we have a 2 by 2 matrix. So let's see that what are the two policies that actually will give us the saddle point solution. Okay, so the optimal estimator is actually follows most of the times a majority rule, okay? And then some other times we actually found that it follows a no consensus rule. And I will explain what is that. Okay, here it is. So we go with the majority except if there is consensus. So again, remember that the worst case is if the attacker actually knows what is the value of x. Okay, so let's say that the detector sees 1, 1, 1. Okay, so with a very small probability, the attacker flip the bits, so we will pick the no consensus rule with a very small probability. Okay. So of course, everything is proven. We have theories for that, and we have guarantees for that. So these are the detector rules. Okay, so the probability is given here. Okay, and of course now we can also say about the attacker rules. Okay, so the attacker actually picks deception or not deception. Okay, so what I mean by deception is when x is 0, okay, so he sets all sensors to 1, and when x equals 1, he sets all sensors to 0. The attack to 1, okay? And of course the non-deception is, as I told you, you remember, that sometimes he might confuse you, okay? So when x equals to 0, he sets all sensors to 0, and when x equals 1, he sets all sensors to 1.
Why the attacker would do that? If he knows x, why he wouldn't take the first part always? Okay, so remember that we also have stochastic errors, right? So the stochastic errors actually might give you more mistakes than you think. So he will try to confuse you in that sense. So let's say that all my stochastic errors gave me, let's say, the wrong event on all this one, okay? And then I have some bits that if he changes, he will actually give me consensus. So, I mean, there are some tricks there yeah, so these are proven to be the saddle point. And so, let's see what else. Yeah, so of course, this works for a specific probability of attack and a specific probability of sensor errors in number of sensors. Okay, so now we will do the general case. Okay, so this was the first step. And we actually reduced this huge matrix to a 2 by 2, but we had some assumptions. So in the next step, so this is just an illustration, so you see, for probability of attack and for different kinds of sensors. Just not that interesting. But now let's go to the interesting part. So we have the general case, okay? So we want to estimate a random variable x, again, based on a measurement z. So now, instead of flipping bits, the attacker and the defender, they actually pick distributions. So, let's say that I have no attack, okay? So, if I have no attack, then I have a distribution R, okay? So, if I have an attack, so then I have something plus the attack, okay? So, the attacker distribution actually is selected by the attacker, okay? Which is a known class. Of course, always the attacker has some limitation, okay? So, you will see what kind of limitations. Okay, so now, we will just have some small example here so you can understand how this works. I will actually connect it to the previous part now, okay? But then I will make it more general. So you will see that this is the general case, and actually it can reduce to also the previous one.
Why is S different than R?
Okay.
Because the attacker chooses when to attack.
Yes, choose where and what to put there.
No, what, yes, it's the A.
Yes.
But why the S is different than R?
Okay, so, I mean, we can consider it similar to R. Yeah. I mean, just some different notation. But yeah, it's up.
No, if it is different than R systematically, that would mean that the attacker may choose when to attack.
Yes.
Under different, and so when he attacks, the distribution is different than in the normal case, and not in the normal, but in the case where he doesn't attack. That would be a reason to be different.
So, okay. So what I mean there, okay, so because let's say that you take, I ask you a question now, okay. So let's say that I connect it to the previous case, okay.
So if I don't have any attacks, so that I don't have any M components there, so it's full of, it's M, right? So let's say the number of sensors, okay? But now, if I have attacks, then this will change. So the S will be N minus M, okay? So I have to take outside the non-attack components and then have the N.
How do I know the non-attack component?
Oh, I don't know, you will see it soon, yeah. So this is just the case, mathematically formulated. I don't know where he attacked, I don't know what he did. But I know that he can attack up to M sensors, okay? So if I know that he can attack up to M sensors, then he can attack from, let's say, from 0 to M. I don't know how many, I don't know where. Okay, so the R, let's say, is N. If the event is x equals to 1, and I have no errors, then of course R equals to N for x equals 1, and then I can just report what I have observed. If there are non-attacked sensors, then of course N minus M will actually see x equals 1 and 0 x equals to 0. And as you see, so the set A, or the probability A, is actually from 0 to N. I don't know what is that. And the attacker actually decides the number of sensors that he will, that they will report x equals 1. Okay? Okay, so now let's actually take the probabilities. Okay, so we want to estimate this random variable x based on a measurement. Okay, so of course this is the general case that I just described. So now we assume that the attacker is in A, B, and the distributions R and S are Gaussian. Okay, so and then we assume that this happens here. Okay, I'm sure the notation is sigma is the variance and all these things, and A and B are actually the parts of the bounds of the attacker. So let's say the usual case, the bound I know it's from 0 to M, so I just put these numbers there.
So R is the distribution that describes the measurements
Without being attacked.
given the fact that they have not been attacked.
Exactly.
Okay, and it is Gaussian with mean rho x and
Yes.
standard deviation
Sigma.
And S is a condition distribution of the measurements given that they have been attacked. Or
Yes.
at least M of them.
Yes.
Most M of them have been attacked.
Yes.
And it is also Gaussian with what mean? A different mean than R?
Yes. So it is actually, let's see what I have put there.
The
Yes,
notation
so
is kind of confusing there.
Okay, so the mean is actually sigma x, and sigma is the other one. So this is what we found there. So so the mean is actually the variance of the x component. Okay, so if you see Rx is the mean and sigma x is the variance, so you see that it feeds the mean to the variance in the other one. Okay, so as you will expect, again, we will have an optimal estimator as a threshold-like rule. Okay, and then we want to find this zeta star such that we can decide when to put 0 or 1. Okay, so and then of course this is for any arbitrary continuous distributions. And of course, if we want to have discrete distributions, then we cannot guarantee exact saddle point, but we can guarantee we are epsilon far from the saddle point because we will actually approximate the discrete with continuous distributions, as we will see pretty soon. Okay, so, and of course the Z star can be actually by solving this guy here. Okay. Okay, so now I told you the continuous distribution, so now we will actually approximate the continuous with discrete distributions. So of course, the binomial distributions that you saw before can be well approximated by Gaussian distributions. Okay, so I'm sure you're familiar with the Desmoulins Laplace theorem. Okay, so now you remember before that we had specific probability of error. Yes.
In this case, the previous slide, I suppose that the quality of your estimate worsens compared to the case where there is no probability, no possibility of attack. Is that true?
If I have no probability of attack, if it's zero.
If I solve the problem for the classical case, there is no probability of attack, I get some quality of estimates of X.
Yes.
Now, with the possibility of attack, I get different estimates, and I
course.
suppose it is worse than
Yes.
the first one, right?
Yes, of course. So this is mixed policy, so it will come with different probabilities.
So did you somehow calculate how much worse? What does it depend on? Does it depend on the probability of attack? Does
Okay,
it
so
depend on M? Does
yes,
depend-
it depends on, you will share pretty soon, it depends on how many sensors I have, okay? So the more sensors I have, of course, the better quality of signal I will have. Yeah, that's all the probability of error, of course, that's the other.
And M, I suppose also.
Yeah, but the M is fixed, let's say. Let's say that I have a fixed budget.
No, M, the number of sensors that can.
They're attacked, yeah. So, I mean, we will consider the worst case in this scenario. So let's say that we have M. So of course, yeah, if we have only one sensor attack, but you don't know that. So that's why we will consider the worst case in this one. But of course, I mean, if we get.
How do you talk about budget?
Oh, yeah,
Is M
so-
related to budget?
Okay, so let's say that the attacker.
Of the attacker, budget of the attacker.
Yeah, so the budget of the attacker. So, I mean, let's say that I have some sensors. Of course, I have to spend some resources to attack some specific parts. Okay, so now let's go to this one. So you remember that in the previous slide I had this Z star, okay? So now if I approximate the discrete by continuous distributions, so then I will actually find a solution for that. But again, I told you that this doesn't guarantee that we are actually exactly at the saddle point, but we're epsilon far, and we have found a solution for how close we are, and then now you will see this, actually what you said before. So, so small when we have enough sensors, and of course also, this is actually what happens. So you see that the M, of course we assume the worst case here, so we don't assume that it's in the set yet. But the N, as we increase the number of sensors, so you see that this epsilon goes to 0. And then we can actually provide these specific bounds that we're being fooled by an attacker. Okay, so let's see. So let's say that when both events are equal and there are no sensor errors, so the threshold value becomes n over 2. Okay, so this is the classical case for every attack probability, and we obtain the classical majority rule. So this is the classical hypothesis that we said before. Of course, as the probability, the a priori probability deviates from 1/2, on the sensor error increases. So the sensor Z star changes to reflect this a priori information on the probability of sensor error. So this was here. Okay. So, and of course, this here you can see that what I talked to you before, that you approximate this with the Laplace theorem, and as you increase the number of sensors, so this goes through. Okay. Okay. So, and of course, we have also worked on dynamical systems on that, but we won't have time to talk about that. So now let's go to. So what I did now is I detect the event. Okay. So I provided some bounds that actually we can actually guarantee that we're not being fooled by the attacker. Of course, these are probabilities, okay? So now, we will actually change gears and do mitigation. And we will do some learning techniques that we can guarantee that in uncertain environments, in continuous time systems, we're able to mitigate sensor and actuator attacks in dynamical systems now, because before it was type. Okay. So this is the motivation. So learning, control, it can appear in different scenarios. So intelligent control, where neural networks are in the feedback. Reinforcement learning, where you learn based on a reward. Adaptive control, where you have an error and then you want this error to go to 0, and then you want to design adaptive laws to do that, based on that you also have some uncertainty to your system. But of course, you can have structural and unstructural uncertainties. Reinforcement learning can also be solved with actor-critic structures. So what I mean by actor-critic, so the actor is actually your control input, okay? And the critic is how good is your control input, okay? And of course, we want to bring learning together with optimization. And then, optimization, there are different techniques in the literature that do optimization. And these two things, they come together by using dynamic programming, which is solved forward in time and solves the course of conditionality. So this is called approximate dynamic programming. So the other thing that we want to combine is ideas from distributed control. Okay, so I'm sure you're familiar with some consensus algorithm or graph theory, team decision, and all these things. So we're very interested in bringing all these three key areas together. Okay, and let's see how we can do that. Okay, so of course autonomy and learning, they're being very hot terms right now. And so what you want your agents, you need to operate under unforeseen circumstances. So what I mean by that is that you don't know if you're being attacked, you don't know what is happening, you don't know if your physical component will be damaged, you don't know anything about, or you don't know about the disturbances that can appear during operation. And of course we want to develop plug-and-play techniques that they don't need any training a priori, or they don't need a huge computer or computational power to compute things and then put it on board. So of course, we want our system to learn from mistakes and improve performance and efficiency. So we want always to have an optimal criteria that we always want to verify. And of course, since we have distributed algorithms, we want to learn and interact between each other. Okay. So, of course, this is another interesting thing that picture here. So you see in the past we just have some robotic arms, and now with the sensors being better and more computational power, we finally can have some multi-purpose assistants like PR2 or Baxter that they're actually learning, and then they can help at home. Okay. Okay. So we have some patents on some learning techniques, and I probably won't have time to talk about that. So what is learning? So learning is the ability to learn a new task without specifically being programmed for that task. So let me say exactly what is that. So since I'm a controls person, when I talk about specifically trained about that, so let's say that we have optimal control. So optimal control is an offline technique. So you have to have a computer, you have to know the dynamics, you solve the recalculate, let's say, and then you take the metrics and then you put it on the system. Okay? But this assumes that you know the system and then you have to do everything offline. Okay? What happens though when you don't know the system, which is actually most of the cases true. Okay, so we want to self-heal, resist attacks, and everything to be online optimization. We have to adapt to unknown failures and damage and uncertain dynamics. Okay? So this is actually the diagram that we will use in this presentation. So as I told you before, dynamic programming is very useful, but it suffers from the course of dimensionality. Okay? So people from reinforcement learning side or neurodynamic programming side have worked on that, and they have proposed some approximating structures to approximate your controller and to approximate your cost by using probably some, let's say, neural networks such that you can approximate these things without needing to know either the dynamics or without needing to do any offline computation. Okay, so here you can see this is actually every agent that you will see pretty soon will have this uncertain system here, environment. Okay, so you can think about it is the physical part, the physical dynamics, the physics of the system, and also you can consider also the connection between the system. So this is the environment. Okay, so this will be considered totally unknown. And then I have the actor, which is actually the control policy. And then I put the control policy into my system and then I check how good it is. And then based on that, I update my control policy again. Okay. And And then, so we have proposed some these techniques, and then we have been actually all over the news about that. So we can learn from mistake, and then you will see actually the algorithm pretty soon. And of course, I also got an award because of this, because we were probably the first ones that we solved continuous reinforcement learning and approximate programming in continuous state and action spaces. Okay. So usually, up to now, people were performing this approximate programming by using policy iteration and value iteration. So in policy iteration and value iteration, you usually have two steps. Okay. The policy evaluation and the policy improvement. Okay. So what we have managed actually is to do these steps simultaneously in an adaptive control sense. Okay. So we want actually to do that, to apply these techniques to mitigate the effects of cyber-physical attacks in autonomous cyber-physical systems. Okay. So in the techniques that I will show, there are no offline computations, neither knowledge about the system, the physics of the system. Okay, and of course, I mean, these are just some other use. Okay, so now let's see what happens. So let's say I have a system, okay, which is a mixed team system between different, let's say, ground vehicles, aerial vehicles, or different, let's say, human operators, okay? So of course, all these, they can enter, they're very heterogeneous, okay? So what I mean by that is that, I don't know what physics they're bringing into the network. Okay, so they're large, complex, dynamic, and highly nonlinear. Okay. Okay. So of course, so this is some what we have observed in the literature. So most of the attacks assume some knowledge of the system dynamics. We will not assume any knowledge of the system dynamics. So both the operator and the attacker, they will assume that they don't know anything about the dynamics. Of course, up to now, in adaptive control sense, so the work does not have any performances, okay? And of course, the robustness guarantees, they can't guarantee different scenarios and cannot be applied directly to security issues. Of course, so what we have to do is we have to actually implement these components inside our feedback control. So what I mean by that is that we don't want to flood our cyber-physical systems with more sensors and more intelligent devices. Okay? So we want actually to mitigate any potential attacked components by designing intelligently our controller. Okay, so let's see. So this is what I talked before. So now let's actually do some math. So you remember this slide from before. So this is a mixed team of different agents. That I don't know about. So of course we can always model. So let's say that we actually follow an approach in the literature. So how you will approach such problems is you will actually go from this one, you will model this with a graph, and then usually you will actually assume that these systems are mostly linear, okay? So this is what people do in the literature. So let's say you can assume that every component in the network has actually its own dynamics. Okay, so you can assume that AI, XI, PI, UI plus DI, VI. Okay, and or of course you can consider the nonlinear case where you have FXI plus GXI UI plus DXI VI. So, but A, B, and D, they can actually be they're unknown. Okay, or they can be controlled by the attacker, right? So remember, in the cyber-physical security, I told you that the attacker also can change the physics of the system. Okay? So let's say you have an airplane, and the airplane actually loses half of the wing. Okay? So we have actually shown with some collaboration with Georgia Tech that even if you lose half of your wing, you will be able to land safely. Okay? Because you will actually learn and operate with this losing physics of the system. Okay. So of course, we can assume that this is our decision input, so this is the controller. And VI actually can, let's say it is an actuator attack. Okay, so let's say that the attack that changes your actuator inputs. So let's say what I want to do. I want actually to track a leader node. Let's say a reference node. Let's say that I have flying UAVs and I want to track a ground vehicle. Okay. So I want to do that, but I don't know any of the dynamics. So what I want to do, of course, this system actually can include faults in system components, physical attacks, and cyber attacks. As I told you, we will assume that we don't have any knowledge about the physics or the connections. So we also don't know the connections of these components. Okay, so what we want to do, as I told you, is we want everybody to follow the leader, let's say. Okay? So since we want everybody to follow the leader, so we want some error to be zero, right? So this error can be xi minus xj, and then we do that in the neighborhood, okay? Plus gi xi minus x0. So what is that? Is that if I'm connected to the leader, okay, so this gi is 1. If I'm not connected to the leader, this is 0, okay? So in most agents, this is 0, okay? But of course, we won't know that. Okay, so now, let's say what I want to do. So we want, again, to approach such problems with a game. So of course, my controller is the minimizer, and my worst case actuator input is my maximizer. Okay. So what we want to do is we want to assign to every agent in the network a specific distributed performance. Okay. So this is given, let's say, by this guy. So EI is this error that is had before, UI is my actions, and VI is the potential adversarial inputs that I don't know about. Okay? So I want to take this one step ahead, and also I want to penalize also the neighborhood actions. Okay? So, of course, the interpretation for that is that the good player wants to minimize that, but the attacker wants to maximize that. Okay? And of course, similar for the UI, this is our updates. So we want to keep it small, which means smooth transitions. Okay? And the attacker updates, so small means stealth, as I told you before. So of course, the interpretation, because one is a minimizer, the other is a maximizer, so the things should change. Yes, please.
What is the matrix R?
Oh, the R. Oh, these are user-defined. These are user-defined matrices. So you pick it depending on how much you want to penalize your actions. Okay. So and then the gamma is the attenuation level that how can I attenuate my adversarial inputs? Okay. So let's say similar to the buzz that I told before. Okay. So so it's obvious that if you take this, if you put this as a big number, then you're actually making yourself harder to work with. Because also you will also lose stability of the system, right? And also the attacker will lose stealthiness. Okay, so usually how you solve this problem? So you go from the performance, you write the well-known Bellman equation. So the Bellman equation actually is, you can write it in a Hamiltonian form. So what you do with that, you just join the performance, the reward, let's say, which the reward is the one I just described here, right? So all this guy is the reward, okay? And then you adjoin it with the quality dynamic constraints, okay? So here you see this is just the dot, the ODs that we had before. And of course, this is the Lagrange multiplier, and it is proven that we actually can pick the Lagrange multiplier as the gradient of the V with respect to EI. Okay. So this is the classical way to approach such problems. So we had some work ranging from 2010, and then we have actually evolved through time. So if you do min-max optimization in such scenarios, so you will actually take the gradient dhi dui equals to 0. This is the stationary condition, right? And then you will find the optimal control. And if you do the same dhi over dvi, then you will find the worst case adversarial input. Okay. So of course we can prove that all these things are converge to a saddle point. Okay. So we have this theorem that we actually prove everything is going well, but this assumes knowledge of the dynamics. Okay? So we want to take that one step further. As we see here, you see that everything depends on the dynamics. A, B, D, so you can see that it depends on the whole alphabet. Okay, and of course here, you
το UI star
Ναι.
είναι ανεξάρτητο το name BI.
Όχι, γιατί άμα κάνουμε... Ναι, άμα κάνουμε stationarity conditions στο HI, αλλά ναι, so you see that here everything has the dynamics. So, and of course, in order to find this guy here, you need to solve this complicated Bellman equation, or as you call it, Hamilton-Jacobi-Bellman equation. Okay? So of course, for the people that are familiar with Riccati's, so if you take linear systems, this reduces to the Riccati equation. Okay? Okay, so this is a theorem that proves that everything is going well. And, but we will write a system, so we want to go one step ahead, and we want to use ideas from Q-learning. So Q-learning actually was invented by Watkins, and he developed that for stochastic systems evolving with Markov decision processes. So for continuous time systems, it's easy to derive Q functions because, as you saw before in my Hamiltonians, they depend totally on the system dynamics. Okay? So in discrete time case, it's easier because the dynamics, they don't appear in Hamiltonian. Okay? So this is the well-known Watkins algorithm. So he invented a way, so as as you saw before, in order to derive optimal control, we have to define a state-based value function that depends on my state, Vx, let's say. V is the value, and then the argument is x. So what we want to, what Watkins did in the Markov decision processes is he found a way to write action-dependent value functions. So not only the states, let's say S, but also the actions. So you put non-optimal actions, and then you learn an optimal action. So this is how Q-learning works. So you choose your actions, okay? You compute the cost, and then you update your actions. And then this iteration will actually make it better every time. So this is a model-free algorithm, but as I told you, this is actually invented only for Markov decision processes. So transitioning now from Markov decision processes to deterministic systems, that they're actually some cyber-physical systems. So we want actually to find a way to write the value function I told you before. So this was how I derived the Hamiltonian before, okay? I want to find a Q function that depends on my state, on my control, the worst case adversarial input, and the actions and the worst case actions of my neighborhood, okay? Of course, I will take all these things will be worst case. Okay. So of course, we prove that we actually have the same exactly performance of V star with the Q star. Okay, so this is a theorem we have, which actually proves that we don't change the optimization, but we will converge to the same exactly cost. Okay. So, of course, every agent, so instead of solving this VI star, you will solve this QI star. So instead of doing these stationarity conditions in the Hamiltonian that I told you before, dHi dVi equals to 0, dHi dUi equals to 0, so now I will do dQi over dUi equals to 0 and dQi over dVi equals to 0, and then you will see pretty soon. So all actually the uncertain information will actually be coded inside here, okay? But I don't know what's happening there, but I want to find this, okay? So let's see. So, of course, this is what I don't know, okay? So I won't know what dynamics the agents have, and I don't know the global graph. Okay, so now, let's see what happens. So, as I told you, I will not base my optimal policies based on my Hamiltonian anymore, but I will base them on my Q function, okay? My Q function, which actually has the same cost with my value function. Okay, so if you do stationarity conditions now into the Q function, so what you get is this guy. Okay, so there's some components of this Q matrix that I want to eventually find. Okay, so and then of course you can compare it to what I had before, right? That I had my everything. I knew my neighbors. I knew where my my graph was pinned. So I knew where my leader was pinned. I knew B. I knew D. Okay, now you see my policies. They're actually model free. I don't have any information about the model. And then we will see how this works. So of course, now the tricky part is to find the ways to tune these guys, right? So since I don't know them, I have to find a way to approximate them, right? So, and then of course to do that, we will use some approximators or some neural networks to approximate these unknown components, Q, U, Q, U, I, B, I, that actually come from this matrix. Okay, so in order to do that, so as you saw here, let me go here, so my QI, this is actually the ideal one, right? So you see it's quadratic in my state and all my actions, in my neighborhood, of course, okay? So ZI is actually this guy, and QI bar is the unknown components. So of course, I can use Kronecker product, and I can vectorize QI, okay? So I can use Kronecker product between the Z's, and actually I can vectorize QI, okay? And I can vectorize this QI and then find it online. Let's see how we can do that. Okay, so here it is. So the QI that you saw, the huge matrix, is vectorized, and I will name it WIC. Okay? And I put together the ZIs. Okay? So the WIC, they're actually the unknown weights to be learned. And the ZI is all the local information from the state and the actions. And I want to do similar things for my control and my worst case adversarial input. So, so you remember in what I had here is I had these unknown components, right? So again, I want to approximate that with another approximation. And to do that, so this guy will convert to what you saw before, and this guy will convert to the big Q matrix. Okay, similar for the adversarial inputs. Okay. So we had actually we have a patent on that. So we were the first that we actually worked on integral reinforcement learning. So we were the first that we actually found this continuous time equivalence of dynamic programming, and that doesn't have the dynamics. So again, in the discrete time case, you don't have the dynamics, and we want to find this equivalence to the continuous time case. So what we did actually is we actually found a way to do that actually in small intervals. Okay, so we will do that from t minus capital D to t, and we will move that. Okay, and so we also have proved that this guy has the same cost with the infinite horizon cost that I had before. Okay, so now, in order to find the WIC component, so we will use a classical gradient descent function. Okay? So the gradient descent function, as you see, it will depend mostly on my ZIs, where my ZIs is my my state and my actions. Okay? And similar gradient descent for my optimal control and my attacker control teams. Okay? And of course, I will always have an error at the end that eventually will be driven to zero. And when this error is driven to zero, then eventually we will have converged with the optimal solution. And as you see here, what you do actually, you just plug and play these three things in every agent, okay? And then you let it learn. And it will converge without knowing anything about the dynamics to what you saw in the beginning, of this section. And so we prove, of course, everything is going well. We have asymptotically stable equilibrium points. Our policy converges to an equilibrium and all this thing. Okay. And now let's see how this works. Okay. So let's say I have a graph. Okay. And then let's say in the scenario that I have a double second order systems. So let's say that I have an actuator attack, So if I don't apply my method, so you will see that it will blow up. Okay? And so the actuator attacks cannot be mitigated with classic frameworks. So what we want to do, if we apply just what you saw before in these three guys, in every agent in the graph, so you will see that eventually everything will be synchronized. Okay, so let's say that this is the phase plane plot. So I start my agent, this is XY, let's say, okay, this is the XY into this phase. So I have 10 agents, okay, so I start them with different initial conditions. They communicate only with the neighbors. So the leader actually is the green one, okay, so it does like that, at least a Zeus plot. You can consider a marginally stable system. So you see that eventually all the agents, even in the presence of the worst case actuator attacks, without knowing anything about the dynamics, they actually converge to what the leader tells them to do. Okay? And of course, we also prove that they converge to the optimal solution. So this is just the components of the Q function that you saw before. Okay, so of course we have applied that to.
What numbers of iterations are we talking about?
Okay, so this happens in real time, the no iterations. So this is what we have done is like.
Okay, what about bad performance in between?
Oh, we always improve the performance. So we prove that the performance.
So every iteration you guarantee improvement?
Yes, but it's not actually iteration. So it's actually, you can think about, so it's not actually policy iteration. Probably you're confused with policy iteration, that you do policy iteration and every policy you improve. So we do these two steps simultaneously in an adaptive control sense. So,
Which is continuous time?
yes, continuous time, continuous state space, continuous action. So everything happens like just doing the ODs. You can consider just the ODs. There are no iterations. And we prove stability.
Yeah, but there is transition nevertheless. So transition can be.
Yeah. You mean during the transit, right? Yeah. Okay. So yeah, if I zoom that, you will see what happens. So there's some transient, and also we have added some resistant excitation, some noise. So this noise can actually help us move away from locking in. And then this actually, you will see some oscillation in the beginning. But yeah, that's a good observation. And then after that we found everybody and we agreed on the value of the agents. They actually, after that, they reached steady state. And they did that. And so we prove, of course, the performance of the proof is infinite time, essentially. So we can prove from time convergence or optimality. Okay, so I mean, this is just an interesting application. I'm sure most of you are familiar with. There's no reason to talk about the dynamics, but so there's similar things. Okay, so you remember the best control and worst case adversary, all these things. So this is just adapted to the helicopter, to only one agent, let's say. Okay. So this is what we got from the simulation, and then you will see what we got from the experiment. So we say to the helicopter to do online, without knowing the nonlinear dynamics, to track a trajectory, okay, to go from here and then track this trajectory. So this is the simulation. So this is the adversary, what the adversary does. So you can see that the adversary actually doesn't stay very small. You can see this is not exponentially decreasing disturbance on adversary that can guarantee different things in robustness. Here, the adversary does crazy things, okay? And so now, probably here, you can see actually what you're talking about, right? So you see this is how they learned, and after they learned, they're actually eventually converged. So this is the simulation. So even in the presence of this actuator attacks, we're able to track the trajectory in an optimal sense. Okay, so let's see how this happens in an experimental application. Okay, so what I want to do is I want to track a trajectory. Okay, so this is just a simple trajectory, I have some attacks. Okay, so whenever you see a bump, it's actually the mitigation is going on. Okay, so even in the presence of, let's say, sinusoid-looking attacks, we were able to track desired trajectories of in translational state transition in transitional states and velocities,
and of course the angular velocity. And all these things you see, they're actually pretty well tracked even in the presence of attacks. Okay? So you see there's some small bumps, but they're very negligible. And then of course after that, we know that there's an attack and then we mitigate it. And so probably I think this is one of the few works that they can guarantee optimal tracking of trajectory in the presence of attacks. So finally, just 5 minutes more. So I told you about detection, I told you about mitigation. So another interesting thing is jamming attacks. Okay? So of course jamming is when you actually try to ruin the communication between different agents, or the communication between the agent and the cloud, or different things like that. So let's say a simplistic case. So you have, let's say, some agents, and the agents want to stay together, okay, in flock, okay? And the jammer wants to break the link, okay? So it doesn't allow the agents to flock, okay? So, I mean, you can assume for this, so for simplistic presentation, I used that integrator here because the equations will get pretty messy. Okay, so of course now I don't have a fixed graph, but I have a time varying graph. Okay, so because the agents will change topologies to avoid the jam. Okay, you can consider that probably as a perturbation game for those of you who are familiar with such games. Okay. Okay, so now of course we have to set some rules of how the graph is constructed. So the graph is constructed based on game proximity. What I mean is that I have some radius that I can see, okay? And then when I see in this radius, I just make a link, okay? So, and of course, this is position dependent, okay? And, okay, so what we want to do is we want actually to formulate that as a zero-sum game. In other words, we want actually to, the agents want to maintain their formation, and outside, let's say, some stop set. So this stop set actually are the rules that they tell me when the game stops. Okay? In other words, is when the controller loses the game. Okay? So I want actually to stay outside of this stop set. And the jammer wants to get me in the stop set as soon as possible. So of course the stop set we can define, let's say, it is the first time, or other rules if you want, the first time that the jammer breaks a link and succeeds to break a link. Okay? So this is, let's say, the stop set when the game stops. Okay, and of course you can always write that as different things, but now, so now we don't have an infinite horizon game, but we have a finite horizon game. Okay? So we will actually formulate that as, again, the agents in the team, they want to maximize the time that they're together such that they flock, okay? And they stay away from the stop set, which actually makes them lose the game. And the jammer actually is the player that actually wants to minimize this time. So now it's a maximum time in a finite horizon sense. So of course, now, before, the agents were reaching steady state, and the optimal solution was steady state. So now, you can think that you solve time-varying equations. So if you had, let's say, linear system, let's say, so this can be a linear system, but it's actually non-linear because we have this proximity graphs. So let's say you have linear systems, so your Riccati won't be steady state. It will be time-varying Riccati. Okay? And you have to have boundary conditions to boundary problem, and then you solve it. Okay. So of course, this rho here is actually the term that will make us take care of the time. Okay. So of course you can see that this is rho t minus t0, right? And so I want actually to do this game, but I want to keep small my actions and my floating, let's say, state. Okay. And okay, so these are just some rules that we have to do for the game. So as I told you, the stop set, which is actually the set that makes the game stops and the controller loses the game. So we want actually to find these rules. Okay. So first, we want to make the rules that the graph stays connected at each time. So you will see it's connected when my k proximity graphs are not validated, and also when I'm not jumped by the attacker. So remember that the 2n plus 1 is the jump. Okay? And eta, the eta that you see here, is actually the strength of the jamming signal. Okay? Okay, so now this is the game here. Okay, so I want to maximize, so the team wants to maximize the time, and the jammer wants to minimize this time. Okay? So of course this is also, oh yeah, so this is just the stop set, and these are the controller and the jammer policies. So this is a nonlinear case, nonlinear problem, which actually has, it's a finite horizon problem. So you can't reach steady state. So you have to do other tricks here. Of course, yeah. So now the neighborhood is not static as before; it's dynamic. Okay. So you change you change neighbors all the time, and so we can use similar as before. So of course, now we have to assume different things. So the performance now, the cost that we will converge, will not be only that, but we will have some extra terms here that actually will take care of the time. And of course, we can guarantee that we're stable. The systems are asymptotically stable, and the polish convert to a saddle point, and all these things. And then let's see how this works. So let's say we have 1, 2, 3, 4, 5 agents. Okay, and then with the blue, and we have a jammer with the green. Okay, so the jammer, we assume that because, let's say, if he doesn't know anything about where the agents are, he will just go their own direction, so there's no reason for the game. So what he does is actually he steals information. He sees the closest agent, so he steals information, and he knows where the thing is going. Okay? So let's say in this scenario, he steals information from this agent, probably it is agent number 1. Okay? So, and let's see how this happens now. Okay, so this is the initial configuration. Okay? So of course, the intuition tells us that the team has to go very close together so they don't have big links so the attacker cannot attack, right? Because if they start in this framework here, they have more space for the attacker to attack, right? Because the attacker actually wants to break the links, okay? So if they come close together and become one point, it won't be easy for the attacker to do anything, because actually I will see where my neighbors, and then I can just operate like that. So, and then, so this is what the intuition told us. So, and actually, if we, when we run our algorithm, actually does that. So you see here that the agents move, this is the trajectories of the agent in the XY plane. So they move, they become one point, and then of course after that, I mean, the attacker is able to just break the link, but it doesn't make any sense because the agents are already one point. Okay. So here you see the distances. So you see that the distances, they're becoming close to 0. Okay. And so this is the time that, of course, the attacker broke the link. But it didn't really hurt us because we got our mission done. And of course, you see here that the agents, they changed everything, and what I just told you about the job. So we just talked about different scenarios. So this is my conclusion. So I talked about stochastic sensors with potential manipulation. We did extension of the results to a large number of sensors, probability of sensor errors, and probability of attack. We generalized the problem. We defined model-free algorithms that they can take into account actuator attacks, sensor attacks and faults, and of course only with local information.
We have shown experiments with accelerator attacks on UAVs, and we also saw some jamming attacks. So the last one I didn't have time to talk about. So we have worked on different things. Okay. So in our work, we solve Hamilton-Jacobi equations that they need to be offline, solved offline. We solve them online. Actually, we don't solve them, but we converge the solution of these equations by using approximate programming. We have applied such techniques in renewable energy. So we have a product, and it led to a startup on a small inverter. So the startup is based in DC. So we have actually currently 4 employees. And we have used different techniques. We have used experience replay to learn attacker capabilities. We have done visualization for cybersecurity situational awareness, event trigger control, human in the loop with vendor experiments, different things. Okay, of course, there are lots of things open in such autonomous systems and learning capabilities. So recently we got interested also in robotic hands. So we have actually a prototype on the bionic hand, which actually is tendon-like, it's inspired. So we want to apply learning how to grasp and do different everyday things. And this very will be in human ones actually now. And other different things that I'm sure I don't want to keep you more here. I'm sure most of you will meet later, so we will talk. And so some results, we actually ended up with 2 books, and we have funding from different agencies. And yeah, so if you're interested in knowing more about my work, of course you can visit my website, or you can even send me an email. And yeah. Thank you very much.
I don't know if you have more questions. It's 12:30, but
I'm sure we will talk. Thank you very much. Thank you for being here.
Dope.